welcome back. So let's continue the discussion, and we have finished turbulent premix flame and the modeling of that, and now we will move to the discussion on turbulent non-premix flame. So as you can see or you recap from this particular diagram, we started off reactive scalars and we did the discussions on transported PDF approach, statistical methods, simple models like EBU, EDM, finite rate chemistry, EDC. Now these are the models which are applicable. Again, applicable does not mean they are going to be accurate, but they can be applied to any mode of the combustions with their associated pros and cons. And then there are models which are very specific to the premix combustion that we have discussed in details, how one develop those models and what are the issues behind that, what is the theoretical background or these things. Now we move to the turbulent non-premix combustion. Now these models are also very specific to the turbulent non-premix case. Now just to give you an idea how this typical turbulent non-premix flame looks like. So this is quite different from the principle of operation of the premix flame, because premix flame, your fuel and oxidizer, they are premixed before they are sent to the or injected to the combustion chamber. But in this case you have the combustion chamber where fuel is injected separately, and so this is your fuel, this is your oxidizer, so they come separately, and then inside the chamber they come in contact through the diffusion process or the mixing takes place, and then the reaction along the stoichiometric line. So this is a basic difference between only premixed to non-premixed, and that is why the flame structures are quite different. Like our other system, these non-premixed flames are basically easy to control, so they are not also dangerous, but obviously there are certain issues which will be associated, like you can see this kind of Eolis flame, which is you have lot of unburnt fuel sitting there. So and also emission becomes an issue, and when you burn hydrocarbon fuel you get carbon and all these things. This is another image where you can see using experimental diagnostic techniques the flame fronts or the images are captured. So this is a very image in the laboratory scale burner, and this is the reaction zone, and this is the overall flame structure. But one thing which is common while talking about the premix flame or the non-premix flame is the importance of the turbulent scales, which are, and that is why we did detailed discussion on the turbulence, their scale, spectra and all these things. Now you can see how this turbulence actually impact this flame front. Now these are some of the examples we have kind of come across this example earlier also, and like your conventional gas turbine which uses in gas turbine in your aviation industry, then your rocket engines, bipropellant rocket engines, your diesel engine, that means glass furnace, boiler furnace, turbojet burners, oil fields, pool flames, combustions and all these things. Now as I mentioned, there are some of the things which are actually can be challenging. One is that, and this is also important to change of depending on the nature of the applications. One is the flame stability, combustion intensity and efficiency, flame shape and size, heat transfer, pollutant emissions. So these are obviously not only problem dependent, these are also dependent on the kind of fuel it is used. So in a nutshell, one can think about they are dependent on the operating conditions, which include not only the geometric conditions, also the flow conditions and other parameters. Now in turbulent non-premix flame, the one of the popular approach is the mixture fraction kind of approach, which is an Conjugate scalar typically denoted by Z, and one has like an progress variable. This is also a non-dimensionalized variable or conserved scalar. This is a scalar variable and which also goes between 0 to 1 from oxidizer to fuel. So, this is how it varies. So, what it allows you, the fraction of the mass present locally which originally is coming from the fuel stream, and for this mixture fraction you have an scalar transport equation without the source term. So, theoretically we solve mass, momentum and species conservation. Now, this species conservation equation, when you convert to in a mixture fraction space, this is again, to mind it, this is an flame normal analysis. This is not one point statistical analysis, this is a flame normal analysis. That means, if you have a flame front like this, so this is your flame normal, where you transform the things in that space and from physical space to that, and you come across the transport equation of this, and this transport equation of the scalar field of mixture fraction, this evolves in the physical space. This is like your unsteady term, this is convection due to mean velocity, this is diffusion. So, there is no source term, which is one of the biggest advantage, because this is the term, chemical source term, which appear in your species mass transfer equation, that creates lot of trouble. I mean, how to close that particular equation, how to close that particular term, and that is why we have seen there are so many variants of different kind of models in different regime to close down that source term. Now, the advantage of this particular conserved scalar approach is that you come across a transport equation, this is without the source term, and you can actually get rid of this chemical source term. So, this is an real advantage, so that the stiffness of the system is reduced, and the boundary condition for that, at the air inlet it would be 0 or oxidizer inlet, and Z equals to 1 in the fuel inlet. An important special value is the stoichiometric condition. Now, in the stoichiometry, if you consider this one step reaction where fuel, oxidizer go to product, your mass stoichiometric ratio is defined as oxidizer by fuel at stoichiometric, which is nu WO by nu F WF, and then you can define the equivalence ratio, which is S into YF by Y0. So, phi 1, which is a stoichiometric condition, phi less than 1 it is a lean condition, and phi greater than 1 could be a rich condition. Now, for a non-premixed flame, an equivalence ratio on the basis of the mass fraction in the incoming stream is defined like phi equals to S into fuel mass fraction to in stream 1 and oxidizer in stream 2. So, the stoichiometric mixture fraction, if one tries to calculate it, it would be 1 by 1 plus phi. So, which is nothing but 1 by 1 plus S YF stream 1 YF stream YO stream 2. So, you can simplify with this expression that we have got earlier. Now, for this single step reaction, now you can take different combination of this, like an equivalence ratio is S into, and then the Z stoichiometry you can find out, and this is heavily dependent on kind of oxidizer you use, and that is what is tabulated here. If you let us say look at pure hydrogen to pure oxygen, this is 1, this is 1, this is 0.5, S would be 8, phi would be 8, stoichiometric is 0.11. At the same time, if you look at pure hydrogen when it is burning with air, Z stoichiometry is quite low, and the reason is you have oxygen now by mass fraction is 0.23, because your oxidizer now contains 77% by mass nitrogen by mass, and this is true for any particular fuel, and that already we have seen while looking at the fundamental flame properties like adiabatic flame temperature and such things, that if you have a fuel which is burning with air and if you have a fuel which is burning with oxygen, they would give you a different flame temperature. So, this table shows you that when different fuel you burn, and now given a fuel you can now calculate these things very easily. So, now we have this single step reaction, we consider this single step reaction, and this is a famous flame structure which is known as Bach-Schumann flame structure. Now, this case is one step, this is a one step reaction, irreversibly infinitely fast chemistry. So, each of these terms, this is one step, irreversible, infinitely fast chemistry. That means fuel oxidizer come in contact, they actually burn and prepare the product. So, if you look at the situation, what happens? So, first let us look at the oxidizer mass fraction. Oxidizer mass fraction, and when it comes to burning state at jet stoichiometric, it would be immediately 0, and this is in the mixture fraction space. So, Y oxidizer mass fraction in Z. Similarly, fuel mass fraction, if you look at it, this is 1 at the beginning, when the reaction takes place it is Z 0, and this lines corresponds to equilibrium line, and this is the mixing line. That means if there is nothing happens, the mixing line will like that, and this is the same mixing line for the oxidizer. Now, if you look at the temperature, this is oxidizer temperature and fuel temperature. Along jet stoichiometric there would be a peak, this is your adiabatic flame temperature, and these are the lines, equilibrium line. So, one can looking at a particular Z value and can find out the temperature at different location. So, this is true simple analysis for one step reactions, where you get this irreversible one step infinitely fast reaction, and that time the temperature profile would be like that, and knowing or by knowing a particular mixture fraction value, one can always estimate the temperature, fuel concentration, oxidizer concentration and everything. Now, if we do little bit detailed analysis of this Bach-Schumann flame equations, so our fuel side, which is Z greater than Z stoichiometric, if you go back here, this is the Z stoichiometric and this is our fuel side. So, the fuel side YF would be Z into YF stream 1 plus Z minus 1 stream 2 S. So, which can be simplified YF stream 1 Z minus Z stoichiometric 1 by Z1. So, this is how you simplify that. Oxidizer at that Z is 0, that because beyond Z stoichiometric oxygen is always 0, and temperature would be Z into T of stream 1 and 1 minus Z T into streams 2 plus Q YF stream 1 by Cp and this. So, this will come the contribution from the stream 1, this is the stream 2, that is oxidizer stream, fuel stream, and this is because of the reaction, the amount of heat which is released. Now, similarly on the oxidizer side, which is Z less than Z stoichiometric, that means this zone, there fuel would be completely 0, oxidizer can be estimated as OA stream 2 Z stoichiometric by Z into by Z stoichiometric, and Tz is Z T stream 1 by this. So, Q is the heat released by combustion of 1 kg of fuel. Now, one can also get the local flame temperature or the maximum local flame temperature, adiabatic flame temperature in the Bach-Schumann kind of model. So, the T adiabatic would be T at Z stoichiometric, which is nothing but Z stoichiometric into T stream 1, 1 minus Z stoichiometric stream 2 into Q stream 1 Cp Z stoichiometric, and Z stoichiometry is 1 by 1 phi. So, if you use that, so this one actually reduces to this equation where T adiabatic can be estimated as 1 by 1 phi into temperature of stream 1 stream 2 into phi by the heat release effect. So, that means these theoretical calculations allow you to estimate the adiabatic flame temperature for any fuel for the global reaction which assumed to be. So, this is now we can have a situation where your equation system is again single step, but it is now reversible, but still infinitely fast. So, previously the case was you have a one step reaction where it is irreversible, but infinitely fast. Now, this case we take it as an one step reaction, but reversible, that means the product can dissociate to form fuel and oxidizer. Now, what happens? If you look at the plot of the oxidizer in the mixture fraction space, this is how it varies. Instead, at the jet stoichiometry where the reaction lies, there is a nice curvature you can see instead of that stiffness, and these are the mixing lines which correspond to that. Similarly, fuel mass fraction, if you look at, it will come down around jet stoichiometric, not that steep, and goes to 0 slowly to oxidizer side. And the temperature would also do not show that peak what we used to or we have seen which is happening at irreversible case. So, compared to that, there is a temperature will be also less, and this is along jet stoichiometry, and these are the mixing line. So, you see immediately there is a change, and that change is coming primarily because of this reversibility, which allows, that means not only this way, that reason is when the product dissociates, that also consumes some of the energy. This side, this part of the reaction can produce, let us say Q1 amount of heat, and this side of this is consumed Q2. So, overall Q would be Q1 minus Q2. So, this is why also that effect is immediately shown in the temperature plot. Now we can look at a case, again is a one step reaction, and this is irreversible and infinitely fast chemistry, where we can comparison between cases infinitely fast chemistry and finite rate chemistry. So, but the reaction is still single step and irreversible. Now, if you recall, if it is infinitely fast, that means fuel oxidizer come in contact and it will produce the product. So, this is our, in mixture fraction phase, this is how oxygen will come at jet stoichiometry, it become immediately 0. Similarly, fuel at jet stoichiometry becomes 0, that means these two guys are come in contact and bond, and the temperature will be peak there, that is for. But when you look at the situation when it is a finite rate chemistry, oxidizer does not come to 0 immediately at jet stoichiometric, rather this goes nicely and then becomes 0. Whereas, if you look at the fuel also similarly, it does not go immediately at 0 at jet stoichiometric, goes like that, and the temperature formation also like that. So, there is a huge impact of the chemistry what you can see even for a diffusion flame, whether it is an. So, that means the assumption that you are going to make, that has lot of impact in your fuel mass fraction and temperature production. So, whether it is a fast chemistry or finite rate chemistry or it is a reversible or irreversible, that will have. Now, we can see this temperature versus jet plot, and we combine this case for a single step reaction which is reversible, and with a situation where laminar flame with chemical mechanism single step, we say fast chemistry which is sort of an equilibrium kind of situation, and there will be finite rate chemistry which is non-equilibrium. If it is fast chemistry, then K goes to infinity. If it is non-equilibrium finite rate chemistry, K is less than infinity. Then one scenario it could be irreversible situation, other situation is the reversible one. And irreversible situation, which is equilibrium, temperature goes up at jet stoichiometry and come to fuel. Now, here when you take the finite rate chemistry, this is the limit of my infinitely fast chemistry limit, this is the finite rate chemistry limit, this is the finite rate chemistry limit, but these two are for different strain. When you have a low strain, you get high temperature, when you are high strain, then you get low temperature. That means now strain has huge impact on flame front. So, this is another important aspect when you look at it. Now, the reversible case, obviously the temperature limit would be less, because of this reversible reaction some of the energy which is again consumed back. Now, if you see, this is infinitely fast chemistry limit, that is still quite high compared to finite rate chemistry limit, and finite rate low strain still produces high temperature, high strain produces low temperature. So, that means when you have high strain, that flame is exposed to that strain. So, the effect of your mixing indirectly impacting the flame front. Now, we will elaborate these things slightly more. So, this is our equilibrium model where K would be infinity. Now, if that is an equilibrium model, that means infinitely fast situation, we can split the whole business into two problems. One is the mixing problem, that means only look at the transport equation of this conserved scalar Zx, and then we can find the equilibrium state for a given Zx from the lookup table. That means the whole reacting system is now broken into two pieces. So, one is the mixing and one other is the reaction with the equilibrium reaction. So, these two combinedly look at the whole flow field. So, this is what happens, and when you find out that table, your species mass function will be equilibrium and the function of Z, temperature also going to be function of Z. This particular concept or the way of handling the system, this works nicely provided you have only presence of two different streams. Second, there is no radiative loss. Third, it is infinitely fast chemistry, equal diffusivity all species. That means this will lead to an assumption of DI is same. It is a sort of a constant DI business. So, these are the sort of an assumption, but these conditions can be relaxed to, we can introduce by introducing more than one mixture fraction. That means we can define another mixture fraction and then can somehow relax this particular inlet issue, and that is what is very common even today. We can define two mixture fraction and solve three stream problem. So, like if we have two mixture fraction, we can solve three stream problem. Then we can add the enthalpy as an independent variable. So, where the radiative heat losses can be taken care of, and also we can generalize into the opposite flamelet model to K less than infinity. So, these are the modifications one can easily do, and now the question comes, how do we evaluate the temperature from mixture fraction? So, that is an important question to answer. So, we have enthalpy, which is an caloric equation of state which gives the enthalpy as a enthalpy of formation plus the other part, where mixture Cp is the total summation of over all the species Yk and Cpk. Now, using the mixture fraction, we can find out the Cp and enthalpy. So, this guy we can find out, and also this guy we can find out. Now, when can enthalpy be obtained from the mixture fraction? So, we use our caloric equation of state and then relate the enthalpy. So, enthalpy is sum over all the species, this is Yk Hk, and for individual enthalpy it is the enthalpy of formation plus the sensible part. And now enthalpy of formation is also individual mass fraction to formation. So, that is the total del F 0 and Cp would be total of this. So, that is what we get H of chemical part and the sensible part for the mixture. Now, for Lewis number 1 case, where the thermal diffusivity and the mass diffusivity they are same. So, once you assume the Lewis number 1 and this is our enthalpy equation, this is what, if you recall, the big we did when we discussed about the governing equation, all this. So, dH by dt, but this is the flux, Q viscous dissipation, then there is a effect due to mass diffusion and the pressure term. So, we neglect this term, this term, this term and this term. So, this will remain. Now, Q will be a contribution due to conduction and this component which we can write in this fashion, del lambda delta t del t and rho hk dk. So, one can expand this side. So, this will remain as it is. This can be taken into two component, one is delta this and dH delta hk. So, finally, we get the flux part is lambda del t rho dH del h rho dH Cp del t. So, then our enthalpy equation becomes rho dH by dt delta dot dH delta h, and we have used dk equals to 1 by Lewis number dH 1 by lambda rho Cp dt. So, delta dot hk would be Cpk delta t. So, this is what we used for unit Lewis number system. Now, you can find out the relation and the mixture fraction. So, you have inlet 1 and you got inlet 2, that is the outlet, and this is our enthalpy equation, mixture enthalpy and steady convection, and this is the diffusion term. This is what exactly we get. Mind it, this is for Lk equals to 1 for that situation, and our normalized scalar on enthalpy would be xi h, which is h minus h1 and h2 minus h1. So, xi h1 would be 0 and xi h2 would be 1. This is how we normalize, so that the xi actually goes between 0 to 1 like your conserved scalar measure. Now, this normalized enthalpy is the same as the mixture fraction provided dz and dh is same. So, we can write h equals to h1 plus z into h2 minus h1. If it is purely at the inlet 1, then it will cancel out, it will be h1, otherwise h2, and in between that varies like that. So, that sort you get in your these things, and you can correlate the enthalpy and the mixture fraction. Now, we go to the turbulent situation where we can look at the mean value, variance and all these things, and we will continue the discussion from there in the next lecture. We will stop here today.